Imagine a tunnel through space, a shortcut that bypasses vast cosmic distances. A wormhole, predicted by Einstein's general relativity, is a theoretical passage in spacetime that could connect distant points almost instantly. It's like carving a tunnel through a mountain instead of taking a long winding road. In theory, wormholes could transport travelers across galaxies, or even to entirely different universes. However, none have been discovered, and their existence remains uncertain. Keeping a wormhole open would likely require exotic matter or negative energy, substances that challenge known physics. Despite these hurdles, wormholes continue to inspire, pushing the boundaries of our understanding of space, time, and the future of exploration. The grand challenge: intergalactic travel in a human lifetime. Intergalactic travel has been a part of science fantasy for a long time, but it is still one of the most interesting and difficult problems in modern astronomy. In everyday life, we can travel long distances in just a few hours or minutes, like when we drive through a mountain tunnel or take a fast train between towns. On the other hand, the gaps between galaxies are so great that it would take millions or even billions of years to travel from one galaxy to another using normal means of transportation. This part goes into more detail about the main problem. How can we possibly try to fit such huge amounts of time into a human lifetime? And how might the idea of a wormhole, which is a theoretical shortcut through space-time, give us hope for making travel between galaxies possible? The speed of light, which is about 300,000 kilometers per second, is not just a high-speed limit. It is also the speed limit of the universe. This is the most important issue in this big task. Einstein's theory of relativity says that in a vacuum, nothing with mass can move faster than light. When we think about how far apart galaxies are, this barrier has very serious effects. The Andromeda Galaxy, which is our nearest neighbor galaxy, is about 2.5 million light-years away. Right now, we don't have the technology to move at the speed of light, so it would still take 2.5 million years to get there. Because people only live about 100 years, these kinds of trips are completely impossible. Imagine the trip as a road trip across a whole continent to help you understand this. Imagine that you have a car that can go an amazing 300 kilometers per hour, but the distance you need to go is the same as going around the world several times. And even at this very high speed, the trip would take too long, and you would be stuck in a car for endless generations. When you're in space, the road is even longer, and the problems are much worse. Conventional ways of moving things, like chemical rockets, or even more powerful ion drives, just can't cover these huge distances in a time frame that works for people. This is where the idea of wormholes comes in as a huge possibility that could change everything. If wormholes exist, they might be able to join two faraway places in space-time, like bridges or tunnels. It is possible for a spaceship to enter one mouth of a wormhole and exit from the other almost instantly, instead of moving through the space between. This shortcut wouldn't be limited by the normal limits of the speed of light because it would skip the distance completely. Imagine folding a long piece of paper in half so that the two ends touch. What was once far apart is now very close to each other. In its simplest form, a wormhole is a way to get through the fabric of the universe faster. The path from theoretical feasibility to actual implementation, however, is fraught with difficulties. To begin with, there is an enormous engineering challenge in either developing or stabilizing wormholes for human travel, even if they do in fact exist. Wormhole theory states that in order to maintain a wormhole open for safe passage, we would need exotic matter or negative energy, which are substances that either do not exist naturally in the amounts needed, or may be beyond our current technological capacity to produce. Wormholes would presumably collapse in a fraction of a second if these unusual materials weren't present, rendering them useless for transportation. The very process of traversing a wormhole introduces additional uncertainties. The intense gravitational forces near the wormhole's entrance, combined with the potential for tidal forces to rip apart any matter passing through, present significant risks. Imagine attempting to drive through a tunnel where the walls are constantly shifting and the forces acting on your vehicle vary unpredictably. It's an analogy that only begins to capture the perilous nature of wormhole traversal. The challenge, then, is not just in the conceptual creation of a shortcut, but in ensuring that it is safe and stable enough to support human life and spacecraft integrity. The energy need is another aspect of this enormous task. It would take an enormous amount of energy to build and maintain a wormhole, even if it were theoretically possible to do so. The most up-to-date calculations using our most accurate theoretical models place the energy on a par with, or even more than, that of a full star. In order to put things in perspective, the Sun produces more energy in 1 second than all of humanity uses in a year. It would require a quantum leap in technology that we have not yet begun to imagine, much less accomplished, to control and steer such a tremendous quantity of energy. Despite these overwhelming challenges, the allure of wormhole travel remains potent. The very idea that we might one day journey across galaxies in mere minutes instead of millions of years challenges the limits of our imagination and our understanding of physics. It forces us to question the boundaries of what is possible and inspires both scientists and engineers to push beyond the confines of our current technology. This vision of rapid intergalactic travel is not just about reaching distant galaxies. It represents a transformative leap in our ability to explore, understand, and ultimately inhabit the cosmos. The philosophical aspect of the great problem of interplanetary travel is there alongside the practical and theoretical ones. The insatiable curiosity of the human spirit to see what is beyond our local horizon has always been a driving force. Exploration has always been an integral component of human nature, from the first explorers to set sail over unknown seas to the most recent astronauts to venture into space. Imagine a future when human race is genuinely intergalactic, not confined to just one planet or even one galaxy. The idea of wormholes as cosmic bypasses appeals to our eternal urge. Contemplating wormhole travel forces us to confront some of the most profound questions about the nature of reality itself. If wormholes are indeed possible, they imply that the fabric of spacetime is far more malleable than we currently understand. This, in turn, could lead to revolutionary insights into the fundamental laws of physics and open up entirely new realms of scientific inquiry. For example, the existence of traversable wormholes might hint at the possibility of parallel universes or other dimensions, adding layers of complexity to our understanding of the cosmos. Even if there are a lot of obstacles, every problem also has a solution. For example, if research into quantum fields and energy manipulation is spurred by the requirement for exotic matter, it might lead to discoveries with implications well beyond wormhole transit. Similarly, innovations in energy storage and generation might be spurred by the massive energy demands, which might eventually have far-reaching consequences for our civilization. Einstein's vision, the birth of spacetime concepts. Albert Einstein's work in the early 20th century revolutionized our understanding of the universe, transforming the way we perceive space, time, and gravity. Prior to Einstein, space and time were regarded as separate static entities, a stage upon which the drama of the universe unfolded. However, with his theory of general relativity, Einstein introduced a radical new idea. Space and time are intertwined in a four-dimensional continuum known as spacetime. This insight not only redefined gravity as the curvature of spacetime, but also laid the foundation for thinking about phenomena that could, in theory, warp or even tunnel through this fabric. The core idea of general relativity is that large bodies deform spacetime in the same way that a big item pressing down on a stretched rubber sheet makes a depression. Gravity is the result of this curvature. Gravity is not a driving force, but rather the outcome of things adhering to the curving pathways caused by the distortion of spacetime. A more comprehensive explanation of planetary motion and gravitational pull was given by this beautiful concept, which also hinted to a world that was more dynamic and adaptable than previously thought. Einstein's revolutionary framework quickly led physicists to consider more exotic configurations of spacetime. One of the most intriguing outcomes of his equations was the theoretical possibility of bridges, or shortcuts through spacetime, later known as wormholes. Initially conceived in the work of Einstein and his colleague Nathan Rosen, these so-called Einstein-Rosen bridges emerged naturally from the mathematics of general relativity. Although Einstein himself was skeptical about the physical reality of such structures, the concept opened up a tantalizing possibility: that the fabric of spacetime might be contorted in such a way that two distant points could be connected by a tunnel-like passage. Consider the cosmos as a huge malleable fabric to better understand this point. Curves and valleys are generated when this fabric is bent and compressed by the presence of a large celestial body, such as a planet or star. It is possible to construct a tunnel between two geographically distant areas by manipulating this fabric or by relying on the fact that nature permits a specific arrangement. An alternative to traveling the standard, linear distance via regular space would be to build such a tunnel, which could connect two locations that would normally be thousands of light years apart. This idea has very important effects. If wormholes could be made stable and passable, they would be able to get around the speed of light limit that normally stops movement. Scientists and science fiction fans alike are interested in this idea because it makes it seem like it might be possible to move long distances between galaxies in a very short amount of time. Einstein's equations are very beautiful, but they also hint at important problems. Most importantly, they show what conditions are needed to keep a wormhole open. The need for what is called exotic matter is one of the main problems with Einstein's theory. There needs to be a type of matter with negative energy density in a wormhole in order for it to stay solid and allow movement. This strange matter would have qualities that go against what we normally know about physics. For example, it would push normal matter away instead of drawing it toward it. Without that substance, a wormhole could form for a short time, but it would dissolve almost immediately, making it useless for any useful trip. Einstein's vision did more than just predict gravitational phenomena. It forced us to rethink the very nature of reality. His insight into the malleability of spacetime has led to decades of theoretical work aimed at understanding whether wormholes could ever be more than a mathematical curiosity. In the decades since Einstein's work, physicists have continued to explore these concepts, refining the equations and investigating the conditions under which a wormhole might be traversable. Researchers have developed various models and simulations, testing the limits of our theoretical understanding and probing the potential of these cosmic shortcuts. Einstein's ideas also have effects that go far beyond wormhole theory. They talk about important things about the universe, like what time is, whether there are alternative worlds, and what will happen to the universe in the end. Einstein's work changed the way we think about gravity by seeing it as a geometric feature of spacetime. This led to the study of cosmology and quantum gravity, which are still growing and challenging our most basic ideas about the world. Einstein-Rosen bridges, the original wormhole model. The concept of the Einstein-Rosen bridge emerged from one of the most iconic papers in theoretical physics. In 1935, Albert Einstein and his colleague Nathan Rosen delved deep into the equations of general relativity and proposed a solution that suggested a natural bridge between two distinct regions of spacetime. This idea, now commonly known as the Einstein-Rosen bridge, laid the theoretical groundwork for what we refer to as wormholes today. The Einstein-Rosen bridge is based on the way general relativity is structured mathematically. Einstein's field equations show how energy and mass change the shape of spacetime. Einstein and Rosen looked at these equations in the context of a charged black hole that doesn't rotate. They found that the answers could be expanded to include two different areas that are linked by a narrow throat, or bridge. It was thought that this bridge would join 2 points in spacetime that would not normally be linked, like a tunnel between two valleys in the mountains. For example, Think of two separate pieces of paper that each reflect a different part of space. By folding the paper in half so that 2 points on different sheets line up perfectly, and then making a tunnel joining these 2 points, you could go from one faraway place to another almost instantly through the tunnel. In a cosmic sense, this is exactly the kind of quick fix that the Einstein-Rosen bridge is. The model was the first mathematical example of how space-time could be linked in a way that goes against the way we usually think about distance, which is in a straight line. The idea is beautiful in terms of math, but there are some big problems with it. One of the main problems with the original Einstein-Rosen model is that the bridge can't be crossed by anyone. To put it simply, if something tried to cross the bridge, it would run into strong tides and unstable conditions that would quickly snap the bridge in two. The event horizon, which is the point past which nothing can go back, is very important in the fall of a black hole. As it was first thought of, the Einstein-Rosen bridge is more of a mathematics curiosity than a useful way to get from one place to another. This limitation stems from the fact that the model does not account for the kind of exotic matter necessary to keep a wormhole open for any appreciable length of time. In classical physics, matter tends to have positive energy density, which contributes to the gravitational pull that can ultimately cause the bridge to collapse. Without a mechanism to counteract this gravitational contraction, any attempt to traverse the bridge would be doomed by its instability. Even with these problems, the Einstein-Rosen bridge is still a very important idea in theoretical physics. This is because it shows that the equations of general relativity naturally allow for links between very far apart parts of spacetime. They made it possible to think about the universe in a whole new way, one in which spacetime is not stiff and unbending, but rather bendable enough to support these strange topological structures. On top of the Einstein-Rosen model, more theoretical work has looked into the conditions under which a wormhole could be made passable. In later research, scientists like Kip Thorne and his colleagues came up with the idea that the wormhole might not break naturally if strange matter with negative energy density was added to the bridge. In these updated models, the wormhole's throat could be kept stable for long enough to allow safe crossing. This would turn the Einstein-Rosen bridge from a temporary event into a possible way to journey between stars or even between galaxies. It is important to note that the Einstein-Rosen bridge occupies a unique place in the evolution of wormhole theory. Although it is not directly applicable for human travel due to its non-traversable nature, it serves as the foundational concept from which later, more refined models have emerged. The notion that spacetime can be connected in non-intuitive ways, allowing for paths that defy classical distances, has inspired generations of physicists to reimagine the limitations imposed by the speed of light. Spacetime as a stretchable fabric. Envision a huge, elastic sheet that extends endlessly in every direction, a surface that isn't hard but rather malleable, capable of deforming anything that lies on it. This is the core of the way contemporary physics conceptualizes spacetime. The fabric of spacetime is not a static set upon which events take place. Rather, it is dynamic and elastic, susceptible to distortion, twisting and stretching in the presence of mass and energy. This view, which forms the basis of Einstein's general theory of relativity, gives us a clue as to how things like wormholes and gravity may come to be. Every time we put a heavy object, like a bowling ball, on a trampoline, we observe the same impact. The ball's mass presses down on the cloth, creating a crease that curves the surface in its vicinity. Afterwards, roll a smaller ball close to the depression's edge, and it will bend inward toward the bowling ball. Planets' orbits around stars are similar in that they are not dictated by an unknown distant force, but rather by the curvature of spacetime due to the star's mass. An object's gravitational attraction and the depth of its dent in spacetime are directly proportional to its mass. This stretchable fabric concept revolutionized our understanding of gravity. Instead of considering gravity as a force that pulls objects together, Einstein's insight allowed us to see gravity as a manifestation of space-time curvature. Every object, whether it's a tiny particle or a massive galaxy, interacts with this fabric. As objects move, they follow paths called geodesics, which are essentially the straightest possible paths within a curved space. The geodesics bend around massive objects, leading to the familiar orbits and trajectories we observe in the universe. When we extend this idea to the realm of wormholes, the stretchable nature of spacetime takes on a whole new level of intrigue. If spacetime is as flexible as a rubber sheet, then it stands to reason that, under the right conditions, it could be manipulated in ways that allow for shortcuts between distant regions. In a wormhole scenario, the fabric of spacetime is thought to be curved or folded so dramatically that two separate points in the universe are brought into close proximity. Instead of traversing the vast distance that normally separates them, an object could pass through a tunnel-like structure, a wormhole, and emerge at the other end almost instantaneously. The picture of bending a rubber sheet isn't without its limitations, though. Spacetime is a continuous four-dimensional surface, not like a flat two-dimensional surface. This implies that time is also a component of any deformation or folding that takes place. The image is complicated by the interaction of space and time, but the basic notion is the same. The curvature is determined by mass and energy, and the trajectories that things travel along are determined by that curvature. The geometry of spacetime isn't set, it can change over time. This is one of the most interesting things that this stretchy cloth means. For example, in astronomy, we see that the universe is getting bigger, which means that spacetime itself is growing. This growth changes not only how far apart galaxies are, but also how light moves through space, which causes things like redshift. These observations strongly suggest that spacetime is a living thing that is always changing and responding to the matter and energy that are inside it. The idea that spacetime is like a stretchy cloth makes it easier to understand strange things that happen in the universe. In recent years, things like gravitational waves, which are ripples in spacetime caused by moving masses faster, have been seen in real life, proving that spacetime does behave like a dynamic, flexible medium. These waves are picked up by tiny changes in the distance between objects, like ripples on a pond. Finding these waves has opened up a whole new way to watch cosmic events, like black holes merging. In the context of wormholes, this dynamic nature is both a blessing and a curse. On one hand, the very flexibility of spacetime suggests that it might be possible to create configurations that connect disparate regions of the universe. On the other hand, the same flexibility means that such configurations could be highly unstable. Just as a stretched rubber band snaps back if overstretched, a wormhole might collapse under its own gravitational tension unless some form of exotic matter is used to keep it open. Exotic matter and negative energy, keeping wormholes open. Using strange matter and negative energy is one of the most puzzling problems in modern physics when trying to turn a potential wormhole into a path that can be traveled through. All known types of matter have positive energy density when things are normal. Gravitational pull is made possible by this positive energy. It makes things stick together, and in the setting of spacetime, curves inward. But in order to keep a wormhole open against its own gravitational pull, something that goes against common sense is needed, a material or energy with negative mass. There is something called negative energy that sounds like something from science fiction, but it is based on the math behind quantum field theory. Sometimes, very small amounts of negative energy have been seen in quantum effects like the Casimir effect. When you put two parallel, uncharged plates very close to each other in a vacuum, the Casimir effect happens. The quantum changes of the electromagnetic field between these plates are limited. This creates a difference in pressure that pushes the plates closer together. This effect could mean that there is negative energy between the plates compared to the space around them. Translating this concept to the scale required for wormhole stabilization, however, is a monumental leap. Theoretically, for a wormhole to remain open and safe for passage, the negative energy must counterbalance the immense gravitational forces that would otherwise cause the tunnel to pinch off. This means that the exotic matter, or negative energy, must be of an enormous magnitude, far beyond what has been observed in laboratory settings. In many theoretical models, the required amount of negative energy is comparable to the mass energy of an entire star, making the practical generation or harnessing of such energy a daunting challenge. Exotic matter has qualities that go against what we normally experience. Classical physics says that things with positive energy are drawn to each other, while things with negative energy would be drawn away if they existed in large amounts. This repellent quality is exactly what would be needed to fight the pull of gravity that makes wormholes fall apart. Strange matter might be able to keep the wormhole's throat open long enough for an object, maybe even a spaceship, to safely pass through by applying pressure outward. Without this opposing force, any new wormhole would probably close in on itself very quickly, making it useless for journey between stars or galaxies. The idea of harnessing negative energy also brings into question the stability of the wormhole structure. Even if one could somehow create a reservoir of exotic matter, maintaining a steady, controlled flow of negative energy poses a significant engineering problem. Fluctuations in the energy density could lead to instabilities that might cause the wormhole to oscillate or collapse unpredictably. In this light, much of the theoretical research into wormholes focuses not only on the existence of exotic matter, but also on how it might be manipulated to produce a stable, traversable structure. Researchers have explored various models in which exotic matter could be incorporated into the fabric of a wormhole. One such model is the Morris-Thorne traversable wormhole, which mathematically demonstrates that a wormhole can remain open if sufficient negative energy is present at its throat. In this model, the negative energy is not distributed uniformly, but is concentrated around the region that requires stabilization. The model serves as a proof of concept, showing that, within the bounds of general relativity and quantum mechanics, the existence of a traversable wormhole is not strictly forbidden, provided that exotic matter exists in the necessary quantities. One of the biggest mysteries in physics is still whether or not strange matter exists. Experiments like the Casimir effect suggest that it might exist on microscopic levels, but it's not easy to bring these effects up to the large sizes needed for wormhole stability. There are some theoretical scientists who say that the universe might naturally have places with negative energy. These could be near certain kinds of black holes, or even in spacetime itself. Others say that new discoveries in quantum field theory and advanced particle physics could one day show how negative energy can be made or increased. The need for exotic matter not only creates technical and building problems, but it also brings up deep psychological and science questions. It makes us rethink what we think we know about energy, matter, and the world itself. Not only is the search for alien matter a way to open up the possibility of traveling between galaxies, it's also a way to learn more about the basic rules that drive everything physical. Traversable versus non-traversable wormholes. Not every wormhole is the same. Some are just interesting mathematical puzzles, while others offer the tempting chance of safe passage. In this section, we explain the difference between wormholes that can't be crossed, they break too quickly for any useful journey, and those that can be crossed, they should be stable enough to let matter pass through. Early models, such as the Einstein-Rosen bridge, showed that wormholes could not be crossed. These wormholes naturally form within the equations of general relativity. However, these shapes are naturally unstable. If you tried to cross them, they would fall apart in a huge way because of the huge forces of tides and gravity. Even though the math makes them possible, wormholes that can't be crossed don't make for safe travel because they close off before anything can get from one end to the other. On the other hand, traversable wormholes are a more complex theoretical idea that needs extra support to keep the tunnel stable. Stopping the pull of gravity that would normally make the structure close is what makes a wormhole safe to travel through. This is where the ideas of exotic matter and negative energy become very important. It might be possible to counteract the gravity pull by adding a controlled amount of strange matter around the opening of the wormhole. This would keep the tube open long enough for a spaceship or any other kind of matter to safely pass through. This balance between negative energy pushing things away and gravitational collapse is very delicate. Even small changes could make the wormhole impossible to pass through again. The concept of shortcuts in space, defining intergalactic travel. The idea of traveling between galaxies is very different from how we normally think about space and time. Most of the time, when we talk about traveling, we mean going from one place to another, or even from one continent to another. But when you look at things on a cosmic size, the lengths are almost impossible to understand. One example is Andromeda, which is about 2.5 million light-years away. Even if light moved at the speed of light, it would take millions of years to travel that far. Using chemical rockets or even more advanced propulsion technologies, the usual ways of going to space can't bridge these gaps in a human lifetime. Before you can fully understand how big the task is, you need to know how cosmic distances work. The universe is very big. The space between stars, let alone galaxies, is measured in light years, which are the 9.46 trillion kilometers that light goes in a year. Imagine going on a road trip where each kilometer means years of travel time instead of just a few minutes on the highway. No matter how powerful conventional ways of propulsion are, they can only go as fast as the speed of light. Einstein's theory of relativity says that this limit is built into the very fabric of space and time. This means that even the most advanced spaceships would not be able to make it across the galaxy if they only used normal thrust. This is where the idea of shortcuts or wormholes enters the discussion. A wormhole, in theory, is like a tunnel that connects two distant regions of the universe, allowing a traveler to bypass the intervening space entirely. Instead of journeying through the conventional linear expanse of space, a spacecraft could theoretically enter one end of a wormhole and emerge almost instantaneously at a far-flung destination. The concept can be likened to folding a vast sheet of paper so that two distant points touch. A tunnel through the fold then connects them directly. In this way, a wormhole would serve as a cosmic shortcut, dramatically reducing travel time and potentially opening up the possibility of intergalactic travel within a human lifetime. The effects of this kind of bypass are huge. It would not only change how we explore space, but it would also make us rethink how we really understand time and distance. It might not take millions of years to travel between planets if there was a wormhole that could connect them. Instead, it might only take minutes or hours, as long as the passage could be fixed and made safe to travel through. Even though this is still just a theory in theoretical physics, it sparks our imaginations and pushes the limits of what we think is possible. To appreciate this transformative idea, consider the current state of space travel. Our most advanced spacecraft are designed for relatively short journeys within our solar system. Even ambitious projects like missions to Mars or the outer planets require years of travel time and come with enormous logistical challenges. The energy requirements, life support systems, and technological demands of such missions are staggering. Now imagine if instead of a prolonged voyage through space, a spacecraft could leverage a wormhole to effectively skip the intervening space, arriving at its destination almost instantaneously. The potential benefits extend beyond merely reducing travel time. They could also alleviate many of the technical and logistical hurdles that currently limit long-duration space missions. It's important to keep in mind that wormholes are an interesting idea in theory, but they are very hard to put into practice. It sounds great to be able to skip through space, but it's hard to make or find a wormhole that is steady and can be traveled through. The need for exotic matter and the need to keep the wormhole throat stable are two big theory and scientific problems that need to be solved. These problems show that wormholes might theoretically be a way to travel quickly through space, but making that idea a reality would take big steps forward that could be decades or even centuries away. Wormholes as time-saving tunnels. As natural paths through the fabric of space-time, Wormholes offer an enticing possibility. They could make traveling between galaxies much faster. The world could be thought of as a huge three-dimensional grid with unseen roads connecting each point. From what we know now, going from one galaxy to another is like taking the long, twisting road through every city and highway in between. This trip takes millions of years. If there is, however, a wormhole, it would act as a tunnel that skips all the space in between, letting people cross cosmic distances in minutes or hours instead of years. This idea hinges on the concept that wormholes are not bound by the conventional rules of linear space. Instead of moving through the empty space between two galaxies, a spacecraft could theoretically enter one end of a wormhole and emerge from the other almost instantaneously. To better illustrate this, imagine folding a sheet of paper so that two distant dots touch. Instead of drawing a line between the dots along the paper's surface, which represents the long route through normal space, you can simply puncture the paper where the dots meet and create a direct path. This is the visual metaphor for wormholes. They fold space, effectively compressing the distance between 2 points that would otherwise be separated by vast expanses of emptiness. The effects of these tunnels that save time are very big. With the technology we have now, no ship can even come close to traveling at a fraction of the speed of light, which is what it takes to travel between galaxies in a human lifetime. It would still take millions of years to get to even the closest galaxies, even if we could move faster than light. There is a theory that wormholes could get around these problems by letting people move instantaneously. A wormhole is a way to go through spacetime that doesn't follow the normal rules. It doesn't limit you by the speed of light in the usual sense. There are some theoretical problems with this possible shortcut. To be a time-saving tube, a wormhole needs to be steady and passable. This brings us back to the important problem of exotic matter and negative energy, which we talked about earlier. To keep the wormhole from collapsing, the throat, or narrowest part of the tube, must be carefully controlled. If there is any unrest in this area, terrible things could happen, like the wormhole pinching off before the trip is over. Additionally, traveling through a wormhole itself creates doubts about how time works. Because relativity says that time is connected to space, going through a wormhole might have strange effects on time. This could show up as time dilation, where a traveler's view of time is very different from someone looking at it from the outside, which makes the idea of instantaneous travel even more difficult to understand. Comparing wormholes with other intergalactic methods. Theoretically, wormholes could help people move between galaxies, even though the lengths between them seem too big to be overcome. They aren't the only idea, however. We look at some other creative ideas and see how they relate to the wormhole idea. These include using hypervelocity stars, time dilation at speeds close to light, and superluminal propulsion systems like the Alcubierre drive. Each method has its own pros, cons, and theoretical problems. This makes them all very different, and it gives us a lot of different ways to think about how we might one day travel through space. The idea of hypervelocity stars is one of the most interesting natural events that has been talked about in terms of traveling between galaxies. These are stars that are thrown out of their home galaxies very quickly because they are close to a supermassive black hole, or because of violent events like supernova explosions. In theory, if a star or a spaceship riding on a star could reach such high speeds, it might be a natural way to travel across very long distances in space. The idea behind this is that the gravity slingshot effect, which is already used in space projects in our solar system, could be made much bigger. However, hypervelocity stars are an interesting natural event, but they are not very useful as means for planned journey. The conditions under which these stars are thrown out are random and wild, and there is no control over where they go. Also, even if someone could control such an event, the harsh conditions near black holes and the powerful forces at work would make any visitors very dangerous. Einstein's theory of relativity, on the other hand, predicts a well-known effect called time dilation, which is another possible way to move between galaxies. If you stand still and watch something move faster than the speed of light, time slows down for that thing. For scientists moving at relativistic speeds, this means that their trip might be much shorter than what someone on Earth would expect. For instance, a trip that seems to last millions of years from Earth might only last a few decades, or even less for the people who are taking it. Experiments have shown that time slows down in many situations, ranging from the rates at which fast-moving particles break apart to the accurate readings made by atomic clocks on fast-moving airplanes. But getting a spaceship to move at speeds close to the speed of light is a huge technological challenge. The amount of energy needed is out of this world, and a spaceship moving at those speeds would have to be strong enough to avoid crashes with interstellar particles, which could be very bad at relativistic speeds. In addition, time dilation can shorten the time it seems like you're traveling, but it doesn't change how far away things are in the universe's rest frame. In this way, time dilation is more of a trick of the mind caused by relativity than a real way to speed through space. Another radical concept is the Alcubierre drive, a theoretical mechanism for faster-than-light travel proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive is based on the idea of expanding space behind a spacecraft and contracting space in front of it, effectively creating a warp bubble that carries the spacecraft along at an effective speed greater than that of light. Unlike conventional travel, the spacecraft itself does not move through space in the traditional sense. Instead, space itself is manipulated to bring distant points closer together. This method circumvents the speed of light limitation because the ship is not moving through space. It is being transported by the deformation of spacetime. The concept is elegant in its simplicity and has captured the imaginations of many science fiction writers and theoretical physicists alike. But the Alcubierre drive is not very good at what it does, both in theory and in real life. These are very important. To make and keep the warp bubble going, you need a lot of strange matter or negative energy. There are times when the Alcubierre drive works well, even though it doesn't follow the rules of normal physics. This works a lot like wormholes that can be crossed. Also, this type of energy might be possible to use, but the drive would likely make huge waves at the edges of the warp bubble, which would be very dangerous for any ship or its people. For the same reason, no one knows how to guide or control a warp bubble yet. This is because the physics behind making space-time shrink or grow on demand are still just guesses. Some studies have also raised concerns about the Alcubierre drive's potential to make mistakes or release harmful energy bursts when it reaches its goal. Nobody really likes the drive, but it's still talked about a lot because it makes us think about how we see the world and what the future of technology might hold. Wormholes, hypervelocity stars, time dilation, and the Alcubierre drive are all different in important ways when we put them next to each other. If wormholes could be crossed, they would connect two faraway places almost instantly, so there would be no need to think about journey time between worlds. While the time dilation and hypervelocity star methods require you to move through space, you do so in a way that changes your sense of time, or in a way that is similar to how things happen in the real world. The Alcubierre drive, on the other hand, wants to change spacetime itself, which is kind of like wormholes. It does this by making a moving warp bubble instead of a tube that stays in one place. Each method is a different way to solve the problem of intergalactic flight, and they all have their own science, engineering, and energy problems. One of the best things about wormholes is that they let you skip long stretches of normal space. Without having to speed up to almost the speed of light, or rely on natural events that are hard to predict, it would be possible to go straight from one galaxy to another if a safe wormhole could be made. This could theoretically allow instant travel, which would totally change how we explore the universe, and could even allow us to talk to or move things between parts of the universe that are currently split by light speed. To make wormhole travel helpful, we need to solve some of the biggest problems in physics. For example, we need to find ways to make the wormhole solid with strange matter and make sure the tube stays open long enough for safe travel. Time dilation, on the other hand, is based on well-known science, but it doesn't actually make places closer together. It just changes how the person experiencing time sees it. On the other hand, a spaceship going close to the speed of light might get there faster, but from the outside, space looks the same huge. This doesn't solve the problem of energy and motion. Hypervelocity. Stars. Natural escape routes from the Milky Way. Hypervelocity stars are stars that are thrown out of their home galaxies at very high speeds. This usually happens when they meet with supermassive black holes or after supernova blasts. In this part, we look at how these celestial events could naturally be used as ways to travel between galaxies, or at least as ideas for such travel. The concept of hypervelocity stars arises from the dynamic gravitational forces at the center of galaxies. When a star ventures too close to a supermassive black hole, it can be flung outwards at speeds high enough to escape the gravitational pull of its host galaxy. This process, sometimes described as a gravitational slingshot, has been observed in multiple instances where stars travel at speeds exceeding 1,000 kilometers per second. The ejection mechanism is not only fascinating from a theoretical standpoint, but also provides a glimpse into the natural extremes of cosmic motion. If harnessed or mimicked in some way, the principles behind hypervelocity stars could potentially be applied to space travel. For instance, a spacecraft designed to take advantage of a gravitational slingshot could, in theory, achieve significant boosts in velocity, allowing it to traverse intergalactic distances more rapidly than conventional propulsion methods would permit. This idea has led some researchers to speculate that, in the distant future, a spacecraft might ride on a hypervelocity star, or at least employ similar gravitational maneuvers, to escape the confines of the Milky Way and venture into intergalactic space. But there are a lot of problems with using hypervelocity stars as vehicles for planned journeys. First, these kinds of stars don't just appear out of nowhere. Their paths are determined by random events in the universe. The path of a hypervelocity star is unpredictable, unlike a controlled propulsion system. This makes it very hard to use its speed for a planned trip. Also, the harsh conditions close to where these stars come from, like the turbulent areas around supermassive black holes, would make it very dangerous for any ship trying to use this event to its advantage. The idea of a gravity slingshot isn't new. Space agencies already use flybys of planets to speed things up, but we don't have the scale of energy or accuracy needed to use hypervelocity stars for intergalactic flight. The physics needed to safely approach, connect to, and then ride the momentum of a hypervelocity star would require huge steps forward in how spaceships are built, how they are navigated, and how they use energy. Time dilation. Traveling at near light speed. Einstein's theory of special relativity led straight to time dilation, which is one of the most interesting and well-studied events in modern physics. This idea says that time is not fixed. Instead, it moves at different speeds for people who are moving in relation to each other. When something gets close to the speed of light, time slows down for that thing compared to a person standing still. This means that a trip that might seem like it requires millions of years from Earth might seem like it would only take a few years, or even just a few months, to someone moving at close to the speed of light. Imagine embarking on a voyage in a spacecraft capable of reaching speeds close to that of light. For the crew on board, the passage of time would be markedly different from the time experienced on Earth. Clocks on the ship would tick slower relative to those on our planet, so while centuries might pass on Earth, the travelers would age only a fraction of that amount. This relativistic effect has been confirmed through experiments with fast-moving particles and precision atomic clocks, underscoring that the phenomenon is not just a theoretical construct, but an observable reality. While time dilation offers a tantalizing escape from the seemingly insurmountable limitations of intergalactic distances, it comes with significant challenges. First, accelerating a spacecraft to near-light speeds requires energy on a scale that is currently beyond our technological capabilities. the energy demands increase dramatically as one approaches the speed of light, meaning that even incremental advances in speed result in exponentially larger energy requirements. Additionally, traveling at such high speeds exposes a spacecraft to the risks of interstellar collisions. Even tiny particles could become lethal projectiles when encountered at relativistic velocities. The visitors and those who stay on Earth will have trouble communicating and staying in sync with each other because of time dilation. When a team comes back from a trip going almost as fast as light, they might find that a lot more time has passed on Earth than they thought. This time gap can have big effects on relationships, the continuation of culture, and even the planning of future missions. Also, we don't really know what the mental and physical effects of staying in a relativistic state for long amounts of time are, because our knowledge of how humans react to extreme situations is still very limited. Despite these obstacles, the concept of time dilation remains a cornerstone of discussions on intergalactic travel. It offers a compelling possibility. While we may not yet be able to reduce the vast physical distances between galaxies, we could, through the manipulation of time itself, make long journeys subjectively bearable. In practical terms, this means that future explorers might experience intergalactic travel not as an eternity of waiting, but as a finite and manageable period, albeit with the caveat that the traveler and the rest of the universe would experience time at drastically different rates. Length contraction, the relativistic shortcut. Envision a long, stiff rod hurtling past a stationary spectator at breakneck speed. If the observer were to follow the rules of length contraction, the measured length of the rod would be less than its actual length, the length when the object is at rest. This effect is a physical result of traveling at great speeds, ingrained in spacetime itself, and not just an optical illusion. The principle of length contraction when applied to intergalactic travel implies that the distance a spaceship needs to traverse, according to its own frame of reference, can be significantly less than the distance a person at rest would have to cover in relation to the galaxies. This relativistic shortcut is a double-edged sword. On one hand, it provides an elegant solution to the problem of cosmic vastness. By simply moving fast enough, a spacecraft might experience a universe that is compacted, effectively reducing millions of light years to a more manageable distance. On the other hand, achieving the speeds necessary for significant length contraction poses enormous technological and energetic challenges. The energy required to accelerate a spacecraft to such high velocities grows exponentially as it approaches the speed of light. Moreover, even if these speeds were attainable, the journey would subject the spacecraft and its occupants to extreme physical conditions and potential hazards from collisions with interstellar particles, which become much more dangerous at relativistic speeds. The divergence in viewpoint between the traveler and an outside observer is another feature of length contraction that makes its implementation more difficult. The crew of the spacecraft may think the distance is less than it actually is, but Earth-based observers would continue to record the entire, uncontracted distance between galaxies. The nature of reality and the ways in which various frames of reference can produce radically different perceptions of time and space are intriguing topics that this disparity brings up. While space explorers may experience a shorter trip in their own time, any attempt to communicate or synchronize with Earth or any other external system would have to take relativity into consideration. Superluminal propulsion, the Alcubierre drive concept. In terms of theory, the Alcubierre drive is one of the most daring and interesting ideas for traveling faster than light. The Alcubierre drive doesn't focus on moving a spaceship through space in the usual way. Instead, it imagines a way to bend spacetime itself. By making space smaller in front of the spaceship and bigger behind it, a warp bubble is formed that successfully travels the ship over very long distances at speeds faster than light, without breaking the cosmic speed limit in any one area. This idea, which comes from general relativity, gets around the usual barrier by changing the shape of space instead of speeding the ship through it. Einstein's field equations can be solved mathematically to show that spacetime can be changed to make a bubble whose inside stays flat and undistorted. This is what the Alcubierre drive is all about. The spaceship would be safe inside this bubble, away from the strong tides that come with traveling at almost the speed of light. Outside the bubble, space is warped so that it gets smaller in front of the ship and bigger behind it. This lets the bubble move through the world as if it were riding on the waves of spacetime. The practical realization of the Alcubierre drive is laden with formidable challenges. Foremost among these is the requirement for enormous amounts of exotic matter or negative energy to generate and sustain the warp bubble. The energy scales involved are astronomical, with some estimates suggesting that the mass-energy equivalent of a planet or even a star might be necessary. Additionally, the mechanics of initiating, controlling, and eventually dissipating such a warp bubble remain purely speculative at this stage. There are also unresolved questions about potential side effects, such as the creation of hazardous radiation or the generation of destructive shock waves when the bubble is turned off. Comparing superluminal methods to wormhole travel. If you compare the possibilities of wormhole travel to those of superluminal propulsion systems like the Alcubierre drive, you can see that each has its own benefits and problems. In theory, wormhole travel could provide a permanent, tunnel-like path through the fabric of spacetime, removing the distance between two faraway places. On the other hand, superluminal propulsion methods like the Alcubierre drive aim to change spacetime itself in real time, making a moving warp bubble that can carry a ship over very long distances. The guarantee of almost instantaneous flight is one of the best things about wormhole travel. As soon as a steady, passable wormhole is created, a spaceship could enter at one end and come out at the other almost right away. This way of traveling doesn't need to speed up to almost the speed of light, so it might not have to deal with the huge energy hurdles and relativistic effects that are problems with other methods. But the problems are very tough. To keep a wormhole open, a lot of strange matter and negative energy would be needed. And even if that strange matter were available, physics still doesn't know how to control and stabilize the wormhole. Superluminal methods, exemplified by the Alcubierre drive, take a different route by proposing a controlled deformation of spacetime. Here, the spacecraft itself remains in a locally flat region, a warp bubble, while space is contracted in front of it and expanded behind it. This method circumvents the relativistic speed limit, not by moving faster than light through space, but by moving space around the craft. The drive's potential to generate effective speeds beyond that of light is tantalizing, yet it too demands exotic forms of energy and faces practical issues such as managing the enormous energy output and ensuring the stability of the warp bubble. Moreover, both methods must contend with issues related to the generation and control of negative energy, as well as the potential for harmful side effects, such as radiation or destructive shock waves upon deactivation. Comparing the two, wormhole travel offers the appeal of a fixed shortcut that, once accessed, requires no further manipulation of spacetime during the journey. However, this set-and-forget approach depends on finding or creating a wormhole that is not only stable, but also strategically located to connect the desired regions of the cosmos. In contrast, the Alcubierre drive's warp bubble is an active mechanism, one that would need to be continuously managed and controlled throughout the journey. While this could allow for more flexibility in choosing travel routes, it also introduces an additional layer of complexity and risk. From an engineering perspective, both approaches present daunting challenges. Wormhole travel might demand a profound breakthrough in our ability to manipulate spacetime on a macro scale, essentially requiring a method to generate and sustain exotic matter in quantities that far exceed current technological capabilities. Meanwhile, the Alcubierre drive requires the harnessing of colossal energy resources and the development of materials or mechanisms that can endure the extreme conditions of a warp bubble. The energy demands for both methods are staggering, potentially requiring energy levels comparable to those produced by entire stars or galaxies. The effect on the traveler's experience is another important thing to think about. Wormhole travel, if it works, could possibly allow a smooth journey from one part of space to another, with only a small amount of the dangers that come with fast travel. In contrast, even if a spaceship is in a warp bubble, it might still have to deal with complicated gravitational dynamics at the bubble's edges. There is also a chance that time and space will be warped, which could make it harder to navigate and communicate with the outside world. Wormhole solutions in Einstein's equations. Gravitation theory rests on Einstein's field equations, which have captivated scientists for decades due to the wormhole solutions they include. Wormholes, or tunnels that connect different parts of spacetime, are discussed in this section as a potential outcome of general relativity's mathematical framework. We examine the many theories and solutions put out over the years, focusing on the circumstances that give rise to these theoretical entities and talking about what this means for stability and traversability. Starting with Einstein's field equations, which connect space-time geometry to energy and mass distribution, the voyage starts. The concise form of these equations is known as the Einstein field equation, EFE, or simply the Einstein equation of general relativity. Here, G mu nu represents the curvature of space-time, while T mu nu describes the energy, momentum, and pressure of matter and fields. Solving these equations, even in their most basic forms, produces famous structures like black holes or an expanding cosmos. Physicists have discovered solutions suggesting the existence of bridges in spacetime, now known as wormholes, by exploring exotic configurations of T mu nu and applying non-standard boundary conditions. One of the earliest and most influential wormhole solutions was derived by Einstein and Rosen in 1935, leading to what is known as the Einstein-Rosen bridge. In this model, a black hole is connected to a white hole, its time-reverse counterpart, through a tunnel-like structure. Although the original Einstein-Rosen bridge is not traversable, it pinches off too quickly for any matter to pass through. It demonstrated that the equations of general relativity naturally allow for the formation of such topological features. The mathematical form of this solution involves a coordinate transformation that doubles the region outside the black hole, effectively creating two asymptotically flat spacetimes connected by a narrow throat. Subsequent work by other researchers, notably Morris and Thorne in the late 1980s, advanced the concept by proposing models for traversable wormholes. The Morris-Thorne wormhole is designed explicitly to be stable enough to allow passage from one region of spacetime to another. Their approach involves constructing a static, spherically symmetric metric, which leads directly to the necessity for exotic matter, as the energy conditions derived from the Einstein field equations are violated in such a configuration. The Morris-Thorne answer is very helpful because it shows that general relativity does not rule out wormholes, but it does have very strict rules about the type of matter and energy that are needed to support them. The null energy condition, NEC, and other energy conditions are usually observed in classical physics. This means that energy levels are either positive or zero. However, these conditions must be broken for a traversable wormhole to stay open, which means that negative energy densities exist. Mathematically, the violation of the energy conditions can be expressed by considering the components of the stress-energy tensor in the wormhole metric. For example, near the throat of a traversable wormhole, the NEC is found to be violated. Such a violation is not possible with conventional forms of matter and radiation, hence the need to invoke exotic matter. In theoretical models, exotic matter might be thought of as a substance with repulsive gravitational properties that can counteract the intense gravitational forces trying to close the wormhole. Although no macroscopic form of exotic matter has been conclusively observed, its mathematical necessity is a direct consequence of the wormhole solutions. The importance of boundary conditions is another important part of these methods. To find a wormhole solution, one usually matches an inside solution that shows the wormhole mouth to an outside solution that is asymptotically flat, or de Sitter if you're thinking about a cosmological constant. This matching process is very important because it makes sure that the wormhole links two different parts of spacetime in a way that makes sense physically. To keep the geometry from having singularities or breaks, the continuity conditions across the boundary must be met. These conditions often dictate the precise form of the functions phi of r and b of r. The mathematical exploration of wormholes has also led to a host of generalizations. Researchers have investigated rotating wormholes, dynamic wormholes, and even wormholes in higher dimensional spacetimes, each with its own set of equations and physical interpretations. For example, adding rotation to a wormhole metric introduces additional complexity, as one must account for frame dragging effects and the possibility of ergo regions, areas where no static observer can exist. Such rotating solutions are still largely speculative, but they offer a richer tapestry of possible behaviors that might more closely mimic the complexities of the actual universe. Advanced computational techniques, including numerical relativity and quantum simulations, are now being used to study the stability of these wormhole solutions. By simulating the dynamics of spacetime under various conditions, scientists hope to determine whether a stable, traversable wormhole is a viable solution to Einstein's equations or merely a mathematical curiosity. Quantum computing is beginning to play a role in these investigations, offering the potential to handle the immense computational load required to model such complex systems. Energy conditions and their violations. A lot of physics theories are based on the idea that energy should be positive. This idea is summed up in a number of energy conditions. There are also the strong and dominant energy conditions, SEC and DC, which make it even harder for matter and energy to behave when gravity forces are acting on them. These conditions aren't just niceties in math. They help make sure that the answers to Einstein's equations lead to spacetimes that make sense literally, where gravity doesn't act in a way that pushes things away normally. Traversable wormholes, however, present a unique challenge. The very geometry that allows a wormhole to serve as a shortcut through spacetime requires that the gravitational forces trying to collapse the wormhole's throat be counteracted. To achieve this, the wormhole must be threaded with a form of matter that exhibits negative energy density. In other words, near the throat of a traversable wormhole, the energy conditions, particularly the NEC, must be violated. Mathematically, evaluating this quantity near the throat using the Morris-Thorne wormhole metric reveals that it becomes negative. This violation is not an arbitrary artifact, but a necessary condition to maintain the open geometry of the wormhole against the crushing effects of gravitational collapse. For a wormhole to remain traversable, however, the negative energy required is vastly larger in magnitude. Theoretical models suggest that to keep the throat of a wormhole open, one would need an exotic form of matter with negative energy density sufficient to counterbalance the immense gravitational forces. This exotic matter would have repulsive gravitational properties, effectively pushing outward against the inward pull of normal matter and gravity. Without such a substance, any attempt to stabilize a wormhole would result in the throat pinching off almost immediately, rendering the wormhole non-traversable. The violation of energy conditions, particularly the NEC, is not just a technical detail, but represents a significant departure from the behavior of all known classical forms of matter. In conventional settings, energy conditions are expected to hold, ensuring that the gravitational attraction is always positive, and that singularities, points of infinite density, can be avoided in certain scenarios. When these conditions are violated, it challenges our fundamental understanding of what is physically possible in the universe. This is why the search for, or creation of exotic matter, remains one of the most formidable obstacles in the quest for practical wormhole travel. The mathematical exploration of these violations reveals deeper insights into the structure of spacetime. Consider, for example, a simple energy-momentum tensor in a region of spacetime. If one were to insert a metric designed to represent a wormhole, analysis of the Einstein field equations would show that, to maintain an open throat, the eigenvalues of the energy-momentum tensor must include negative values. This is a direct manifestation of the requirement that the energy conditions be violated in the wormhole's vicinity. Researchers have proposed several models to quantify the amount of exotic matter needed. In many scenarios, the required negative energy density is of an order of magnitude that pushes the limits of even the most optimistic extrapolations from quantum effects. Quantum field theory's insights on wormhole stability. Given that these conditions are very difficult, the idea of negative energy opens up an interesting area for more study. It makes me think that our present classical intuition, which says that energy is always positive, might not be enough to fully understand how complicated the world is at the quantum level. As quantum field theory, quantum gravity, and experimental physics make progress, we might find new states of matter that can naturally break the energy conditions in a controlled way. These kinds of discoveries would not only change the way we think about wormhole physics, but they might also have huge effects on how we think about astronomy and high-energy physics in general. In wormhole physics, the quantum vacuum plays a dual role. On one hand, the inherent fluctuations in vacuum energy can, under certain circumstances, generate the exotic negative energy required to counteract gravitational collapse. On the other hand, these same fluctuations can introduce instabilities, as they may cause the energy density around a wormhole to vary unpredictably. The challenge, therefore, lies in finding a balance, ensuring that the quantum effects contribute to a stable configuration rather than triggering rapid collapse. The idea of quantum inequalities is one potential path that experts are looking into. Because of these imbalances, there are limits on how much and how long negative energy can stay in a certain area of spacetime. So, quantum fluctuations can make areas of negative energy, but they are usually limited in how strong they are and how long they can last. To keep the wormhole mouth from closing, any negative energy must be carefully spread out and kept up in order for the wormhole to be navigable. It's possible to keep a wormhole going for a long enough time to allow safe travel, according to theoretical models. This is because quantum fluctuations can be controlled or managed. Modern computer methods are now being used to model how spacetime behaves around a wormhole in terms of quantum mechanics. These simulations use both classical general relativity and quantum corrections to give a fuller picture of the situations in which a wormhole might stay stable. Early findings from these kinds of studies show that the vacuum's natural quantum noise is a major threat to stability. However, it's possible to lessen these effects either by carefully adding more fields or creating boundary conditions that stop fluctuations that make the system less stable. Another interesting thing that QFT has taught us is what role other quantum phenomena, like how gravity and entanglement interact, might play. Some theories say that the entanglement of quantum states across a wormhole might actually help keep it stable by making connections that stop energy changes that are too big of a problem. These ideas are still just guesses, but they show how quantum physics and general relativity interact in a rich and complicated way. This is an area where our knowledge is still growing. It's also important to keep in mind that the new information from QFT doesn't provide a complete answer to the problem of wormhole stability. Instead, it just makes what is possible more likely. The idea that quantum effects might be able to both make a wormhole less stable and more stable at the same time adds a dynamic and uncertain element to the idea. From this point of view, a wormhole might not be a fixed structure but rather something that changes over time. Its ability to act as a root relies on how well the quantum forces are balanced. One of the busiest areas of theoretical physics right now is the search for this balance. Cosmic strings and their potential role in stabilizing wormholes. Cosmic strings are made-up ideas about one-dimensional topological flaws that might have formed during phase changes in the early universe. Some great unified theories predict these very thin but very dense strands of energy. In theory, they could have a big effect on gravity over very long distances. The next part of this article talks about the idea that cosmic strings might help keep wormholes stable by supporting them in space and keeping the throat open against the pull of gravity. The idea behind cosmic strings contributing to wormhole stability stems from their unique gravitational properties. Due to their enormous mass per unit length, cosmic strings would create strong, localized distortions in spacetime. The gravitational field around a cosmic string is peculiar. It induces a conical geometry in the surrounding space, meaning that if you were to travel around the string, you would experience a deficit angle, a small, missing piece of spacetime. This unusual geometry could, under the right conditions, help counteract the forces that tend to close a wormhole, potentially serving as a stabilizing structure. One theory says that if a cosmic string were to run through the throat of a wormhole, the string's gravity pull could stop the wormhole from collapsing inward as it normally would. In this arrangement, the cosmic string could hold the shape and make sure it stays open so it is safe to move through. This idea is very much just a guess, but it does offer an interesting way that natural cosmic events might help solve one of the most difficult problems in wormhole physics. Researchers have explored various mathematical models to assess this possibility. These models often involve complex interactions between the energy-momentum tensor of the cosmic string and that of the exotic matter required to stabilize a wormhole. Early results suggest that, in certain cases, the presence of a cosmic string can indeed modify the spacetime curvature in a way that favors stability, potentially reducing the amount of exotic matter needed. However, such models remain theoretical and hinge on many assumptions about the properties and existence of cosmic strings, a subject that is still very much open to experimental verification. The potential role of cosmic strings in stabilizing wormholes also raises broader questions about the nature of spacetime and the interplay between different types of cosmic defects. If cosmic strings exist and can influence wormhole stability, they might also provide observable signatures that could be detected through gravitational lensing or other astrophysical phenomena. This possibility links the study of wormholes with ongoing efforts in observational cosmology, suggesting that future discoveries about cosmic strings could indirectly support the viability of traversable wormholes. Mathematical models: the Morris-Thorne traversable wormhole. The Morris-Thorne model is one of the most influential and detailed theoretical frameworks for describing a traversable wormhole. Developed in the late 1980s by physicists Michael Morris and Kip Thorne, this model was designed not merely as a mathematical curiosity, but with the practical goal of outlining conditions under which a wormhole could be safely navigated by travelers. Central to the Morris-Thorne wormhole is a metric that describes a static, spherically symmetric spacetime with a throat connecting two separate regions. The model introduces two key functions: the redshift function, which ensures that no event horizons form, thus keeping the wormhole open for passage, and the shape function, which determines the spatial geometry of the wormhole and its throat. These mathematical requirements inherently lead to a violation of the energy conditions, as sustaining such a geometry demands the presence of exotic matter with negative energy density. In the Morris-Thorne wormhole, the stress-energy tensor calculated from the metric shows that, near the throat, the null energy condition, NEC, is violated. This violation is not simply a mathematical inconvenience, but a necessary feature that allows the wormhole to resist gravitational collapse. While such matter is not observed in everyday physics, quantum phenomena like the Casimir effect hint at the possibility of negative energy under certain conditions, thereby lending a measure of plausibility to the model. In the field of wormhole physics, the Morris-Thorne model is a major step forward because it connects abstract theory to a situation that could theoretically allow movement between stars or galaxies. It gives a clear goal for theory, and maybe even future actual research, by laying out the geometric and physical requirements for a wormhole that can be traversed. Scientists are still looking into this model and its variations, trying to find ways to change it so that it doesn't need as much unusual matter, or so that it can work in certain astrophysical situations. Simulations and quantum computing in wormhole research. These days, we can't study the complicated science of wormholes without using modern computer tools. We will talk about how numerical simulations and new quantum computing methods are being used to model and test how stable and how wormholes move in this part. Researchers can use these models to mix the basic equations of general relativity with quantum corrections. This gives them a more complete picture of how a wormhole might act in real life. Simulations in numerical relativity have enabled scientists to study the nonlinear evolution of spacetime geometries that include wormhole-like structures. By discretizing Einstein's field equations on powerful supercomputers, researchers can model scenarios in which exotic matter is used to stabilize a wormhole throat. These models help in visualizing how fluctuations in the exotic matter distribution, as well as the inevitable quantum noise, might affect the overall stability of the wormhole. For instance, by tweaking parameters in the Morris-Thorne metric, simulations have been able to demonstrate conditions under which a wormhole could, in principle, remain open long enough for safe traversal, even if only momentarily. Alongside classical simulations, quantum computing is emerging as a promising tool to tackle the immense complexity inherent in wormhole research. Quantum computers excel at handling problems with exponentially large state spaces, a feature that makes them well suited for simulating quantum field theory effects in curved spacetime. Researchers are beginning to explore how quantum algorithms can be used to simulate the behavior of spacetime at scales where classical computing struggles. These quantum simulations aim to incorporate the subtle interplay between quantum fluctuations and the curvature of spacetime, offering insights into whether controlled negative energy states could be maintained to support a traversable wormhole. For example, recent work has focused on using quantum simulation frameworks to model the Casimir effect and other vacuum phenomena that produce negative energy densities. By extending these models, scientists hope to predict how such negative energy might be harnessed or sustained in a macroscopic wormhole. While these simulations are still in their infancy, they provide a crucial bridge between theoretical predictions and potential experimental verification. The goal is not only to confirm the mathematical plausibility of traversable wormholes, but also to identify specific signatures or behaviors that could be targeted in future observational or laboratory experiments. Researchers can use these advanced computer methods to try out different starting points and boundary conditions that might lead to stable wormhole solutions. Scientists can make a stability landscape for wormholes by running many models. This helps them find places in the parameter space where the wormhole might not need as much unusual matter or where it stays stable when things move around it. This methodical study is very important for figuring out if wormhole flight is possible in the real world and for leading future theoretical advances. Creating or locating a wormhole. Theoretical methods. One of the first things that needs to be done to move between galaxies is to get access to a wormhole, which can be done by either making one artificially or finding one that already exists. Theoretical methods suggest two main ways to do things. The first one includes making a wormhole artificially using cutting-edge technologies that can change reality on a huge scale. To do this, you would need to know a lot about quantum gravity and be able to focus huge amounts of energy in a very controlled way. Particle accelerators or other high-energy systems could be used to cause a limited shift in spacetime. At the moment, we are not able to do something like that, because it would probably require energy levels similar to those of star events. The second approach focuses on locating naturally occurring wormholes in the cosmos. Some astrophysical theories suggest that wormholes might form spontaneously in regions with extreme gravitational fields, such as near black holes or in the early universe during phase transitions. Detecting these wormholes would require novel observational techniques, such as analyzing anomalous gravitational lensing effects or unusual star orbits that indicate a hidden shortcut in space-time. Advanced telescopes and space-based observatories, coupled with precise measurements of cosmic phenomena, might one day reveal the signatures of a natural wormhole. There are big problems with both methods. To make something artificial, we would need to have unimaginable power over strange matter and energy. On the other hand, finding new things in nature depends on finding small, indirect signs in the universe. In either case, the project pushes the limits of what scientists and engineers know now and needs big steps forward in both theoretical physics and real-world technology. As study goes on, scientists are looking into these options through a mix of theoretical studies, computer simulations, and experiments that try to find the most extreme conditions where wormholes could exist. Stabilizing a wormhole. Engineering with exotic matter. One of the hardest mechanical problems we face is making a wormhole stable enough for flight. Even if someone found or made a wormhole, it would be very unstable in its normal state and would likely fall apart quickly because of gravity. To keep the mouth of a wormhole open long enough for safe travel, these gravity forces must be fought with exotic matter, which is matter that has a negative energy density. This part talks about the theoretical reasons for this need, the engineering difficulties of working with such strange matter, and the possible future technologies that could help us make wormholes stable enough to journey between galaxies. The main problem with stability is that wormholes tend to pinch off, which needs to be avoided. In traditional models, the tube would break almost instantly if nothing was done to stop the pull of gravity on the wormhole's walls. Travel would be impossible. Adding exotic matter, which has negative energy and gravity qualities that push things away, could be the answer. When negative energy is present, it pushes things away from the wormhole, which can counteract the pulling force of gravity. The Morris-Thorne model, for example, shows theoretically that a wormhole can only be traversable if the stress energy tensor near the wormhole doesn't follow the normal energy rules, specifically the null energy condition, NEC. Although the engineering task is not easy, in real life, the first problem is making or getting enough unusual matter. With the technology we have now, negative energy has only been seen in very small amounts through quantum effects like the Casimir effect. We can't do the experiments we need to do right now to see if we can scale these effects up to make a large area of negative energy that could keep a wormhole stable. To focus and manage negative energy, we would need new ways to do it. This could be done by using advanced quantum field management or states of matter that naturally have these qualities that we haven't found yet. Another significant challenge lies in the distribution and maintenance of exotic matter within the wormhole structure. Theoretically, exotic matter would need to be precisely arranged around the wormhole's throat to create the required counteracting force. Even slight fluctuations in the density or distribution of this matter could lead to instabilities, causing the wormhole to collapse unexpectedly. This necessitates the development of advanced control systems, potentially leveraging breakthroughs in nanotechnology, quantum sensors, and real-time feedback mechanisms that can monitor and adjust the exotic matter configuration continuously. Also, the amount of energy needed for this kind of stability is huge. Some models say that the negative energy that might be needed could be as big as or even bigger than the mass energy of a star. To safely reach and maintain this amount of energy, huge steps forward would need to be taken in how energy is produced, stored, and managed. In the long run, these needs might need to be met by ideas like controlled fusion, antimatter reactors, or completely new types of energy. In addition to the production and control of exotic matter, the integration of such a stabilization system with the spacecraft presents its own set of engineering challenges. The interface between the wormhole and the spacecraft must be designed to handle the extreme gravitational gradients and tidal forces present at the wormhole's boundaries. The craft would need specialized shielding and structural reinforcements to protect both the vehicle and its occupants from the potentially violent fluctuations in spacetime curvature. Additionally, navigation systems would have to be extraordinarily precise, capable of guiding the vessel through a dynamic and possibly unpredictable wormhole environment. The field of theoretical study keeps pushing the limits of what is possible when it comes to stabilizing wormholes. Not only are researchers looking into the mathematical requirements for a stable structure, but they are also looking into lab models that might be able to behave like wormholes on a smaller scale. Quantum computing and numerical simulations have come a long way, which is very important to these efforts, because they let scientists model the complex interactions between strange matter and the structure of spacetime in a controlled way. With enough technical progress, these models give us hope that one day we might be able to create a stabilization system that makes it possible to travel through wormholes. Navigational and structural challenges. Navigating through a wormhole is not as simple as merely having an open passageway. It also demands overcoming significant structural and navigational hurdles that stem from the extreme nature of spacetime distortions. In this subsection, we explore the complexities of steering a spacecraft through a wormhole's turbulent environment and ensuring that both the vehicle and its occupants remain safe throughout the journey. Before anything else, a wormhole's shape is very different from that of flat space. As a spaceship gets closer to a wormhole, it comes across a part of spacetime that is not only bent, but also has fast changes in both curvature and gravitational gradients. These changes cause tides that are hard to predict and can stretch, squeeze, or even tear apart a ship that wasn't built to handle them. Because of this, engineers need to come up with new building materials and designs that can absorb or resist such strong forces. To fight these effects, ideas like adaptive shielding, active structure dampers, and metamaterials with high durability are being thought of, but putting them into practice is still very hard. The task of navigation within a wormhole is equally daunting. Unlike conventional space travel, where trajectories can be calculated with relative ease using well-established principles of orbital mechanics, the passage through a wormhole requires real-time adjustments in a dynamically shifting spacetime. In a wormhole environment, traditional reference points may disappear or become distorted, making it difficult for onboard instruments to provide accurate positional data. Advanced navigation systems would need to incorporate artificial intelligence and quantum sensors capable of interpreting complex gravitational signals and rapidly recalculating optimal paths through a constantly evolving field. These systems might rely on a network of interlinked beacons or even quantum entanglement to maintain a coherent frame of reference, ensuring that the spacecraft remains on course despite the chaotic backdrop of curved spacetime. At the opening and exit points of a wormhole, there are likely to be a lot of unstable areas. Strong gravity shear forces could act on the edges of the wormhole, where spacetime on the outside meets the tube on the inside. These forces could cause eddies or shock waves that are rough and could make it hard for a spaceship to move through the space. To lower these risks, we would need very advanced predictive models that lets the navigation system see ahead and stay away from possibly dangerous areas. Real-time computer analysis, which might be helped by quantum computing, could keep changing the spacecraft's path to stay away from places where the wormhole's structure becomes unstable or unpredictable. Another structural challenge arises from the need to integrate the spacecraft's design with the unique demands of wormhole traversal. The vehicle must be capable of withstanding not only the external tidal forces, but also the internal stresses induced by rapid acceleration or deceleration as it enters and exits the wormhole. This calls for a redesign of conventional spacecraft architecture, emphasizing both flexibility and robustness. The craft's hull might need to be composed of composite materials that combine high tensile strength with the ability to dissipate energy quickly. Additionally, internal systems, including life support and communications, must be insulated from the disruptive effects of intense gravitational variations. This could involve the development of isolated safe zones within the spacecraft, where sensitive equipment is shielded from external shocks. The combined effects of navigational uncertainty and structural stress also necessitate rigorous testing through simulations and experimental analogues. Researchers are employing advanced numerical simulations to model the intricate dynamics of a spacecraft moving through a wormhole. These simulations integrate the equations of general relativity with material science and fluid dynamics to predict how different design choices might fare under extreme conditions. By testing various scenarios in virtual environments, engineers can identify potential weaknesses in a spacecraft's design and refine the technology needed for safe passage. Energy requirements: powering a wormhole traversal. One of the greatest obstacles to achieving practical interplanetary travel is powering a wormhole traverse. The energy needed to build and maintain a wormhole that can be traveled through is enormous, maybe on par with or even higher than the total energy output of a star. In this part, we go into the scope of these energy needs, the potential theoretical sources that may meet them, and the technological advancements that could be required to efficiently collect and channel this energy. Creating enough exotic matter or negative energy to stabilize the wormhole's throat is the fundamental need of the challenge. Keeping one's mouth open in the face of crushing gravitational forces necessitates an unfathomably high level of energy input, according to theoretical models derived from the Morris-Thorne framework and others. Chemical, nuclear, or even the most advanced fusion technologies already in use fall well short of the demands. The alternative is that severe astronomical events such as gamma-ray bursts or the tremendous production of quasars might one day need energy harvesting. Although there are enormous technological hurdles to overcome in order to capture even a small percentage of the energy emitted by these events, they do hint at what might be achievable in the future, thanks to technological progress. Changing and managing this huge amount of power is another part of the energy issue. Even if a possible way to make the energy were found, it would take a whole new class of energy processors to turn it into a form that can be used to change spacetime. As of now, there is no device in technology that can easily change this kind of high energy flow into the controlled negative energy densities that are needed to stabilize wormholes. A lot of the time, ideas for these kinds of converters involve complex quantum field management, materials that can work in harsh conditions, or even made-up things like tiny black holes that collect energy. Even though these ideas are interesting, they are still very much in the area of theoretical study. The exact balance of energy input is directly linked to how stable the tunnel is. If there isn't enough energy, the wormhole's throat will fall under the force of gravity. If there is too much energy, it could cause catastrophic instability or even uncontrollable distortions of space-time. Real-time tracking and adaptive control systems that can make quick changes in response to changes in the energy field around the wormhole are needed for this delicate balancing act. For these kinds of systems to keep the right amount of energy throughout the trip, they would probably need big steps forward in quantum sensors and fast computer feedback loops. The energy requirements also have implications for spacecraft design. Any vehicle attempting to traverse a wormhole would need an onboard power system robust enough to interface with the wormhole's energy field, ensuring that the craft remains structurally intact and properly aligned with the tunnel. This might involve energy shielding to protect against intense radiation or gravitational waves generated by the energy fluctuations at the wormhole boundaries. Additionally, the integration of these power systems with navigational and communication systems is critical. Any disruption in the energy supply could result in a sudden collapse of the wormhole, jeopardizing the safety of the travelers. Theoretical suggestions also say that using vacuum energy, which is also called zero-point energy, could be another way to meet these energy needs. Quantum space is not empty, it is full of changes that could be used to make useful energy if the conditions are right. But getting the amount of vacuum energy needed to stabilize wormholes is still a long way off. This is because current testing methods can only see its effects indirectly, like in the Casimir effect. Spacecraft designed for extreme environments. Making a spaceship that can handle the rough conditions of wormhole travel is a difficult task that requires many more skills than making a normal spaceship. Gravitational gradients, tidal forces, and radiation levels can rise rapidly in a wormhole, making it a dangerous place to be. The ship must be built with materials and systems that protect both its structure and its people. The first major consideration is the spacecraft's hull. Traditional spacecraft are designed primarily to endure the vacuum of space and occasional micrometeoroid impacts. However, when approaching a wormhole, the vehicle will encounter intense tidal forces caused by the extreme curvature of spacetime. To address this, engineers must explore advanced composite materials that offer exceptional tensile strength and energy absorption capabilities. These materials might include futuristic alloys or metamaterials whose properties can be dynamically adjusted in response to changing gravitational fields. The hull must be capable of flexing without fracturing, allowing it to dissipate the stresses induced by rapid fluctuations in the gravitational environment. Along with the hull's structural stability, the ship needs to have special protection to keep high-energy radiation and gravitational waves away from its systems and people inside. Changes in energy near the throat of a wormhole can cause bursts of radiation and strong gravity waves that are much stronger than what most spaceship shields can handle. Advanced radiation screens, which might use layers of superconducting materials or electromagnetic fields created by systems on board, could block or soak up dangerous radiation. In addition, vibration damping devices and adaptive structure supports could be added to protect against the effects of gravitational waves and keep the spacecraft's life support and sensitive equipment working. Putting together high-precision navigational and control systems is another important part of designing spaceships that can pass through wormholes. As the spaceship moves from normal spacetime into the warped spacetime of a wormhole, standard guidance methods that use set spots in the sky may stop working. To get around this, the craft could have quantum sensors and real-time computer feedback loops that could look at how the gravity field changes in the area around the wormhole. These high-tech systems would keep changing the spacecraft's path so that it stays in line with the wormhole's center axis and stays away from areas with a lot of chaos or structural instability. To stay in touch with outside command centers, even when relativistic effects change the way signals travel, there would also need to be a number of alternative communication systems. The internal environment of the spacecraft must also be engineered to provide a stable, habitable zone for the crew during the potentially prolonged journey. This involves not only robust life support systems capable of operating under variable gravitational conditions, but also ergonomic designs that account for the psychological and physiological impacts of high-speed, relativistic travel. Isolation from the extreme external environment could be achieved through specially designed safe zones within the spacecraft, where critical systems are shielded by additional layers of adaptive materials, and where occupants can retreat from the vibrations and accelerations experienced during wormhole traversal. When it comes to connecting with the wormhole's energy field, the spacecraft's energy control tools are very important. An onboard reactor or energy exchanger that syncs with the wormhole's power needs could be needed for the craft to make a smooth journey through the wormhole and stay stable during the trip. Not only would this system have to power the ship's movement and keep people alive, it would also have to control the energy transfer processes that keep the wormhole's throat open. This is a very difficult engineering problem to solve. Mitigating risks, avoiding tidal forces and structural collapse. In the harsh environment of a wormhole, where the curvature of spacetime can change quickly and gravity gradients are very high, it is very important to keep the ship and its people safe. This section is all about plans and technical solutions that can help lower the risks that come from tidal forces and the chance that structures will fall apart while a wormhole is being traversed. One of the foremost hazards in a wormhole is the intense tidal force, the differential gravitational pull that can stretch or compress a spacecraft unevenly. These forces, which arise from the sharp curvature of spacetime at the wormhole's boundaries, can subject the vessel to severe mechanical stress, potentially leading to catastrophic failure if not properly managed. To counteract these risks, engineers must develop adaptive structural designs that can flex and absorb energy without fracturing. Advanced materials, such as dynamic metamaterials and smart composites, are being explored for their ability to alter their mechanical properties in real time, thereby reducing the impact of sudden tidal variations. The use of active stabilization tools is another important approach. These devices would have groups of sensors and actuators spread out inside the ship. They would constantly check the gravitational field and make quick, real-time changes. These stabilization systems could move loads and counter forces before they reach dangerous levels by detecting changes in water forces and predicting possible stress points. In these kinds of devices, gyroscopic stabilizers, magnetic field generators, and even microthrusters might all work together to keep the ship straight and intact. Energy management is also a very important part of lowering risks. It is possible to tune the same energy systems that power the wormhole passage to lower vibrating energy and keep the spacetime environment around the vessel stable. This design could be used for two different things, so it would need control systems that are very well linked and can sync up energy distribution with structural damping devices. For example, electromagnetic fields could be created around the spaceship to make a bubble that protects it from sudden changes in the tides. This would make the gravity landscape smoother while it is in transit. Extensive simulation and modeling are essential to identify and prepare for the myriad of unpredictable scenarios a spacecraft might encounter. Advanced computational models, leveraging both numerical relativity and quantum simulations, are used to map out potential risk zones within a wormhole. These models help engineers design escape trajectories, identify safe corridors within the wormhole, and establish protocols for emergency maneuvers if the structure shows signs of imminent collapse. In addition to pre-mission simulations, real-time onboard data processing powered by artificial intelligence can continuously update risk assessments and optimize the spacecraft's path, ensuring that the vessel avoids the most hazardous regions. Any design that aims to lower these risks must include redundancy and strong fail-safes. To deal with sudden changes in gravity forces, there must be multiple backup systems in place for both structure support and navigational controls. Multiple contact channels, sensor arrays, and emergency propulsion systems would add important layers of security, making sure that even if one system breaks, the others can keep the task on track. Searching for wormholes, gravitational lensing, and anomalous star orbits. Astronomers have long used indirect ways to find things that they can't see directly, and wormholes are no different. In this part, we look at how gravitational lensing and studying stars with strange paths might be able to show that there are wormholes in the universe. Gravitational lensing happens when a big object bends light from a background source, making multiple pictures or curves that aren't straight. If there was a wormhole in the line of sight between a person and a faraway galaxy, the wormhole's strong curvature of spacetime could cause lensing effects that are different from what we normally see from huge things like galaxies and black holes. For example, a smooth mass distribution might make an arc or Einstein ring, but a wormhole could make strange asymmetric lensing marks or even several separate pictures that are not linked to each other. These strange patterns might be a fingerprint of the strange spacetime shape of a wormhole. So, to find these kinds of strange things, researchers are looking closely at high-resolution astronomy data, which is being collected by tools like the Hubble Space Telescope and, more recently, the James Webb Space Telescope. To try to find these small differences, complex algorithms and machine learning methods are also being used on very large datasets. In addition to gravitational lensing, the orbits of stars around massive objects can offer clues to the presence of a wormhole. In regions where wormholes are hypothesized to exist, the gravitational pull might not correspond to any visible mass. Instead, astronomers might observe stars moving in unexpected patterns or with velocities that defy explanation based on the visible matter present. These anomalous orbits could indicate that an unseen wormhole-like structure is influencing the star's motion. For example, if a group of stars near the galactic center exhibits erratic movements or sudden shifts in trajectory, this might hint at an underlying wormhole distorting the local gravitational field. Current astronomical data, what we've seen so far. Astronomers have gathered a lot of information over the past few decades. Most of it has been read through the lens of standard astronomy, but it also has some intriguing clues that may point to the existence of wormhole-like phenomena. In this part, we look at some of the most important observations and strange things that have come up as we've explored the universe. We'll focus on data from advanced telescopes, studies of how galaxies move, and unexpected gravitational effects. The most compelling sources of observational data comes from gravitational lensing studies. As discussed earlier, gravitational lensing occurs when massive objects bend the light from background sources, producing characteristic distortions such as Einstein rings or multiple images. In recent years, high-resolution observations from telescopes like Hubble and the James Webb Space Telescope have revealed lensing events with unusual characteristics. Some of these events display asymmetries or lensing patterns that do not align with models based solely on visible matter distributions or known dark matter halos. For instance, there have been instances where the lensing effect appears to produce fragmented or seemingly disjointed images that could hint at a complex gravitational field, one that might be generated by a structure with the exotic geometry of a wormhole. Although such interpretations remain speculative, these anomalies invite further scrutiny and suggest that our current models may be incomplete. The study of how stars move around inside galaxies is another interesting topic. When we look closely at stars, especially those that circle the centers of galaxies, we sometimes see movements that are hard to explain with standard gravity dynamics. In some cases, stars have been seen to move along paths or show variations in speed that point to the impact of a gravity source that can't be seen. Many times, these strange events are thought to be caused by dark matter. But there are times when the gravity trace is too localized or short-lived for dark matter models to easily explain. Some experts think that these kinds of differences have led them to suggest that sometimes a wormhole or a similar structure in spacetime might be having an odd gravitational effect, changing the orbits of nearby stars in a small way. Data from radio and X-ray telescopes have also contributed to this discussion. Observations of active galactic nuclei and regions surrounding black holes sometimes display irregular emissions and fluctuations that defy conventional explanation. For example, certain high-energy events have been recorded with characteristics that suggest abrupt changes in the local spacetime curvature, events that, in theory, could be associated with transient wormhole activity. While these signals are often interpreted within the framework of accretion dynamics or jet formations, their occasional irregularities provide a basis for considering alternative explanations, including the possibility of exotic spacetime features. Surveys of the cosmic microwave background (CMB) radiation have also sometimes hinted at strange things that don't fit with normal models of the universe. The main goal of CMB studies is to learn more about the early universe, but some researchers have noticed small changes in temperature and polarization patterns that might be affected by large-scale topological flaws or structures that look like wormholes that formed after the Big Bang. These strange events are on the edge of what we can observe right now, and they can be interpreted in different ways. However, they show that our world may be more complicated than our usual models suggest. Recent advances in data analysis and machine learning have enabled astronomers to re-examine existing datasets with fresh eyes. Algorithms trained to detect unusual patterns in the distribution of matter and light have begun to uncover features that were previously overlooked. These efforts have sparked interest in reinterpreting certain cosmic phenomena, such as unexpected voids, unusual lensing events, and atypical galaxy dynamics in the context of exotic spacetime structures. Although none of these observations provides conclusive evidence for wormholes, they collectively suggest that the cosmos may be more varied and intricate than our current theories predict. Because of this, the current amount of astronomical data is both a task and a chance. On the one hand, many of the strange things that could be seen as proof of wormholes are pretty minor and could have other causes within the normal framework of astrophysics. On the other hand, these strange events make it clear that our knowledge of the world is still scarce. There is a better chance of finding clearer signs of wormhole-like events as observational techniques get better. This is happening because of new cameras, detectors that are more sensitive, and more advanced ways to analyze data. Future missions and telescopes, expanding our cosmic vision. The next wave of space projects and astronomical tools will be very helpful in the search for and study of wormholes. We hope that future telescopes and observational platforms will help us see further into the universe. These will have better resolution, sensitivity, and spectral range, which will let us look more closely at minor gravity effects and strange cosmic events that could be signs of wormholes. Upcoming space-based telescopes are poised to revolutionize our observational capabilities. Instruments like the next-generation James Webb successors and specialized missions designed to probe the high-energy universe will offer unprecedented clarity in the infrared and X-ray regimes. These wavelengths are particularly valuable for observing regions near supermassive black holes and other extreme environments, where the conditions necessary for wormhole formation might exist. By capturing high-resolution images of gravitational lensing events and mapping the intricate motions of stars in galactic cores, these telescopes will refine our models of spacetime curvature and possibly reveal anomalies that could be interpreted as wormhole signatures. Observatories on the ground, like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, are expected to provide data that will support work being done in space. Astronomers will be able to see fine features in the structure of faraway galaxies and the spread of dark matter thanks to their adaptive optics systems and ability to gather a lot of light. This level of accuracy is very important when looking for the small changes in space-time that a wormhole that can be traversed might leave on light sources in the background. These telescopes may also help with long-term studies of how stars move, which could help find strange patterns that might be connected to strange gravity effects. Additionally, a new instrument in our observational toolbox will be future gravitational wave detectors. Ripples in space-time that are characteristic of wormhole dynamics may become visible as our capacity to detect and understand gravitational waves increases. The formation, fluctuation, or collapse of a wormhole might cause it to emit a unique gravitational wave signal, which could be detected by interferometers of the future. The merging of electromagnetic and gravitational wave astronomy will pave the way for a multi-messenger investigation of unusual space-time structures, providing a more complete picture of the cosmos. Along with these technical advances, projects aimed at high-precision astrometry, like those planned for the far future, could completely change how we think about how stars move. Astronomers will be able to find even small changes from expected paths by measuring the positions and moves of stars very precisely. These kinds of changes could indirectly show that wormholes exist, especially if they happen in places where normal theories, like dark matter, don't fit the behavior seen. Creating specialized poles that focus on specific areas of space where theoretical models suggest wormhole formation might be more likely is another interesting idea. Several observational platforms would work together on these specific tasks. They would use wide-field images, spectroscopy, and time domain analysis to record short-lived events and minor lensing effects. Researchers want to make a full map of space-time errors that could lead them to possible wormholes by combining data from different wavelengths and monitoring methods. The future of astronomical observations also rests on advancements in data processing and machine learning. With the enormous volumes of data generated by next-generation telescopes and detectors, sophisticated algorithms will be essential for identifying and classifying unusual features. Machine learning models can be trained to recognize the distinctive patterns expected from wormhole-induced lensing or anomalous stellar dynamics, enabling rapid analysis and reducing the chance of missing critical signals. This integration of artificial intelligence with observational astronomy is expected to dramatically accelerate the pace of discovery. International partnerships and coordinated efforts between private companies, study schools, and space agencies are also making it possible for bigger projects to happen. Sharing resources and knowledge not only improves the technology that can be used, but it also helps build a global scientific group whose goal is to figure out the mysteries of the world. These kinds of partnerships are important for the long-term search for wormholes because they mix different ways of observing and check the results of different tools and platforms. The role of particle accelerators and quantum experiments. In addition to astronomical data, particle reactors and quantum studies can help us understand and maybe even recreate the conditions inside wormholes. In this piece, we look at how controlled lab tests with high-energy particle collisions and advanced quantum technologies can help us understand how to change spacetime, what negative energy densities are, and what kinds of strange matter are needed to keep wormholes stable. At the forefront of this research are particle accelerators, such as the Large Hadron Collider, LHC, which enable scientists to recreate conditions similar to those present just moments after the Big Bang. In these high-energy environments, researchers observe the behavior of subatomic particles and the emergence of phenomena that defy conventional expectations. One key area of interest is the study of vacuum fluctuations and the production of transient negative energy states. Experiments have confirmed effects like the Casimir effect, where two uncharged plates in a vacuum experience an attractive force due to suppressed quantum fluctuations, thereby providing indirect evidence of negative energy. Such insights are crucial because, as theoretical models of wormholes indicate, negative energy is essential for counteracting gravitational collapse and keeping a wormhole traversable. Quantum studies are also very important for studying how quantum physics and gravity work together. Quantum interferometers and sensors are being improved to find tiny changes in spacetime that could point to strange configurations like micro-wormholes or similar things. The accuracy of these measurements is being pushed to its limits, and they might show subtle quantum effects that are hidden by traditional physics. At the same time, researchers are using quantum simulations and early-stage quantum computers to make models of how complex interactions happen in spacetime that is bent. Scientists want to confirm theory statements and find useful factors for wormhole stabilization by modeling the behavior of exotic matter and negative energy in controlled environments. Using very cold atoms and Bose-Einstein condensates in the lab has led to new ways of modeling parts of bent spacetime. You can change these systems to make them behave like gravity fields. They can be used as a testbed for ideas that could one day be used in large-scale wormhole engineering. Even though these analog models aren't really wormholes, they help us understand how to use quantum coherence and negative energy in harsh settings. Advancing our understanding of fundamental physics. The study of what will happen to the world in the end isn't just an academic pursuit. It could lead to huge advances in our knowledge of basic physics. Scientists have to push the limits of existing theories and come up with new models that better describe how matter and energy behave in extreme situations by studying things like the Big Freeze, the Big Rip, and vacuum decay. This part talks about how studying possible endings of the universe is helping us understand particle physics, dark energy, and quantum gravity better, and how these new ideas are changing the basic ideas of modern physics. The need to make general relativity and quantum physics work together is one of the main things that drives this field. The usual way of explaining spacetime, which is based on Einstein's theory, works really well on big sizes, but not so well with quantum phenomena. For situations where the universe ends, like those involving vacuum decay or the slow loss of energy in the Big Freeze, we need a system that can handle both gravity effects and quantum fluctuations. Researchers are making progress in the area of quantum gravity by working on these problems. The goal of this project is not only to bring together the basic forces, but also to explain how spacetime might change states, possibly even changing the basic rules of physics during a cosmic phase change. These investigations likewise revolve around the mysterious dark energy. One of the most baffling aspects of the universe is dark energy, which is believed to be responsible for the universe's rapid expansion. Physicists seek to understand dark energy by studying its effects on models such as the Big Rip. This is being pieced together piecemeal by experiments and observations that monitor the expansion rate of the cosmos, for example, those involving supernovae and the cosmic microwave background. As a result of these endeavors, new theoretical models are being developed which expand upon our current conventional model of cosmology and may, in the long run, lead to a fuller comprehension of the cosmic driving force. The study of how stable particles are in a world that is changing is another important area of study. For example, the idea that protons could decay, which is prophesied by some grand unified theories, has huge effects on what will happen to matter in the long run. Protons might not be truly steady if they break down over very long periods of time. If this is true, then even the most basic building blocks of matter might disappear one day. Experimental physics is being pushed to its limits by studies of proton decay and related phenomena. Detectors are being made to see these very rare events. Not only do these studies test what particle physics says should happen, but they also help us understand how the universe evolved and how it will end in the end due to heat death. Scientists need to look at the idea of vacuum stability again and make it better because of possible cosmic endings. The thought that the state of vacuum we are in now might be metastable raises important questions about how the universe will behave in the future. The idea of quantum fields helps us understand how changes in the void could cause changes in energy states. If these changes ever happened, they could completely change the forces and particles that make up our world. Scientists are learning about new parts of quantum mechanics by looking into these options. These new parts could lead to surprising breakthroughs in high-energy physics and even new technologies for manipulating energy. These cosmic questions have led to theory progress, which is backed up by cutting-edge tests and computer models. High-energy particle reactors, like the Large Hadron Collider, are still looking into the basic properties of matter. At the same time, next-generation observatories and gravitational wave monitors are gathering information about how the universe works on a very large scale that has never been seen before. Quantum computing is also starting to play a part by giving us new ways to model complex quantum field interactions in curved spacetime. This is a very important step toward figuring out how the most extreme conditions in space affect basic physics. Advancing our understanding of fundamental physics. The study of cosmic ending scenarios is more than just anticipating the universe's closing moments. It is a dynamic discipline that actively drives improvements in our knowledge of the fundamental rules regulating reality. Researchers are motivated to push the frontiers of known theories by studying events such as the Big Freeze, Big Rip, and vacuum decay, ultimately enhancing our understanding of particle physics, dark energy, and quantum gravity. When confronted with these extreme possibilities, scientists are forced to reconcile general relativity with quantum mechanics, an attempt that has already resulted in substantial advances in domains such as quantum gravity and string theory. These attempts are critical for developing a unified theory capable of describing the behavior of spacetime under severe situations. One important area where cosmic ending research is having an influence is the study of dark energy. One of the most enigmatic forces in the universe is dark energy, which is assumed to be responsible for the universe's accelerating expansion. By investigating how dark energy may drive a scenario such as the Big Rip, in which the repulsive force finally overcomes all other interactions, physicists are constructing new models that not only explain present findings, but also anticipate the universe's long-term future. This research is broadening our understanding of how basic forces interact on a cosmic scale, perhaps leading to groundbreaking discoveries into the real nature of dark energy itself. The study of vacuum decay and the chance of a phase transition in the vacuum state of the world also challenges what we think we know about how stable things are in quantum field theory. If the vacuum state we're in now is just a false vacuum that can change, then quantum tunneling events could cause a terrible change to a lower energy true vacuum. This option has huge effects on many things, including what will happen to the universe in the end and how matter and energy work at their most basic level. As a result of research in this area, tests are being run to look into the quantum void. These results are leading to new theories that connect high-energy particle physics with cosmology. Finding out how stable matter is another important area of study. The possibility of proton decay, which is a process suggested by some grand unified theories, has huge effects on how long the material world will last. Even though proton decay hasn't been seen yet, studies are pushing the edges of what can be found and making our theories more accurate. Finding out if protons, which are the building blocks of atoms, are truly stable over astronomical timescales is important for getting a full picture of how the universe has changed over time and for figuring out how it might finally reach heat death. Moreover, transforming this discipline are the developments in computational methods, especially the application of quantum computing. With their capacity to replicate intricate quantum field interactions in curved spacetime, quantum computers provide a hopeful path for simulating events that classical computers find difficult. Exploring the interaction between quantum fluctuations and gravitational effects depends on these simulations, which also offer a virtual laboratory where ideas regarding exotic matter and negative energy may be systematically investigated. These simulations provide priceless insights that greatly help to guide experimental plans and improve theoretical models. High-energy particle accelerators, such as the Large Hadron Collider, keep providing essential information that shapes our knowledge of basic physics. These tests let scientists investigate the most fundamental behavior of matter by simulating circumstances like those of the early cosmos. Not only is the continuous research at these facilities testing the validity of our present models, but it also looks for novel particles or interactions that could explain dark energy, vacuum stability, even the conditions required for wormhole stabilization. Technological innovations inspired by cosmic research. Cosmic ending scenarios provide difficulties not limited to theoretical physics, but also stimulate a tsunami of technical developments capable of transforming many disciplines. Investigating the processes behind events like the Big Freeze, Big Rip, and vacuum decay forces researchers to create fresh methods and technologies to see, replicate, and finally use these extreme circumstances. By doing this, cosmic research is pushing developments in computer techniques, materials, science, and energy generation that could have significant effects outside of astrophysics. The necessity to create and control energy on hitherto unheard-of proportions is one of the main technological difficulties resulting from the research of cosmic goals. Theoretical models forecasting events like the Big Rip depend on an awareness of dark energy, a factor driving the universe's fast expansion. Scientists are creating very sensitive tools and detectors able to detect minute changes in the expansion rate of the cosmos in order to investigate dark energy in great detail. These tools not only help us to grasp dark energy, but also open the path for revolutionary developments in energy management systems. Inspired by the necessity to regulate enormous power outputs, developments in energy storage and conversion, for example, may result in new types of reactors or energy harvesting devices that might one day power major engineering projects, both in space and on Earth. Materials science is another field where cosmic study is accelerating technological development. Extreme conditions linked with universe-ending scenarios characterized by strong gravitational fields, radiation, and temperature fluctuations, demand materials with extraordinary endurance and adaptability. New composites and metamaterials resistant to severe stress and dynamically responding to changing environments are under investigation by researchers. Not only are these materials essential for designing spaceships able to withstand the stresses of intergalactic travel, but they also have possible uses in creating safer, more robust infrastructure on Earth. Development of self-healing materials, adaptive insulation systems, and even protective coatings capable of functioning in hostile conditions might result from advances in this discipline. Another frontier being driven by cosmic research is computational technologies, especially in the framework of events like vacuum decay or wormhole stabilization. The intricate models needed to replicate the interaction between quantum mechanics and general relativity are computationally demanding. Scientists are looking to quantum computing, which has the ability to process enormous volumes of data and mimic quantum phenomena in curved spacetime significantly more effectively than conventional computers, increasingly to meet these issues. Along with quickening cosmology research, these developments in computer capability are driving the creation of algorithms and data processing methods applicable across many scientific fields. Over time, the knowledge acquired from these simulations might result in fresh approaches for system optimization, complicated behavior prediction, and even issue resolution in disciplines such as economics and climate science. The technical advancements inspired by cosmic research reach observational methods as well. The search for the fate of the universe has motivated the creation of gravitational wave detectors with hitherto unheard-of sensitivity and resolution, as well as next-generation telescopes. These devices let us see events formerly only theoretical by capturing minute signals from the distant regions of space. Applications for the technology behind these observatories, advanced optics, cryogenics, and vibration isolation, often abound in other fields like medical imaging, remote sensing, and even communication systems. The continual enhancements in these observational instruments keep increasing our capacity to explore the universe. The ensuing data drives more technical advancement as well. Enhancing observational capabilities. Testing and improving the hypotheses explaining the ultimate fate of the cosmos depend on developments in observational technology. Next-generation telescopes, gravitational wave detectors, and creative quantum sensors are poised to transform our capacity to see cosmic events in this area. These devices will not only enable us to explore further into the early universe, but also record the faint signals linked with universe-ending events, such minute changes in dark energy or transitory gravitational anomalies. Emerging space-based observatories, successors to instruments like the James Webb Space Telescope, will offer unprecedented sensitivity and resolution across multiple wavelengths. Enhanced infrared capabilities will allow us to peer into the universe's formative years, capturing the light from the first galaxies and mapping the distribution of matter with remarkable precision. These observations are essential for constraining models of cosmic expansion and for understanding the role of dark energy in shaping the universe's long-term evolution. Simultaneously, improvements in spectroscopic techniques will enable more accurate measurements of redshifts, helping scientists to chart the rate at which the universe is expanding and to detect any deviations that might signal new physics. On the ground, advanced observatories such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will complement space-based efforts. Their massive apertures and cutting-edge adaptive optic systems will provide detailed images of distant cosmic structures, allowing us to resolve individual stars in nearby galaxies and to map the intricate gravitational fields that may indicate the presence of exotic phenomena. These facilities will also play a crucial role in long-term surveys of galaxy dynamics, offering insights into how gravitational interactions evolve over billions of years. Another frontier ready to greatly improve our observational capacity is gravitational wave astronomy. Scientists may now listen to the waves in space-time produced by cataclysmic cosmic events using detectors including LIGO, Virgo, and forthcoming next-generation interferometers. Within the framework of universe-ending events, these waves may exhibit marks of dramatic transitions, that is, the emergence or collapse of a wormhole, or even abrupt changes in the vacuum state. Combining electromagnetic observations with gravitational wave data in multi-messenger astronomy will give a more complete knowledge of these occurrences, and help us to cross-verify theoretical predictions with observed events. Analyzing enormous volumes of observational data is changing as artificial intelligence and machine learning are included into data processing pipelines. Terabytes of data may be sieved by sophisticated algorithms to find minute irregularities and patterns that might otherwise go undetectable. These computational instruments are especially helpful in spotting unusual occurrences or small-scale characteristics suggestive of novel physics, therefore hastening the rate of discovery and improving our theories of cosmic development. Future missions and experimental programs. Several missions aiming at increasing our observational capacity are already in development on the space-based front. Designed to run over a wider spectrum of electromagnetic wavelengths, from infrared to X-rays, new telescopes and observatories will offer closer views into the early cosmos. These devices seek to record the weak afterglows of the Big Bang, track the development of dark energy, and see until unheard-of clear creation of large-scale cosmic structures. Successors to the James Webb Space Telescope, for instance, promise to push the limits of sensitivity and resolution, allowing the discovery of faint signals suggesting the long-term fate of the cosmos. At the same time, next-generation gravity wave devices will change the way we listen to the universe. Using what LIGO and Virgo have learned, better interferometers are being made that are more sensitive and can pick up a wider range of frequencies. These devices will be able to pick up gravitational waves from more than just black holes merging and neutron stars colliding. They will also be able to pick up waves from events that are thought to be connected to things that could end the universe, like sudden phase changes or the fall of strange cosmic structures. Using electromagnetic and gravitational wave data together, which is sometimes called multi-messenger astronomy, will give us a fuller picture of these very rare events. Experiments in the lab are also going to be very important. Particle engines like the Large Hadron Collider are still looking into the building blocks of matter, and new facilities are trying to make conditions like they were in the beginning of the world. These tests are very important for checking how well theories about vacuum stability, negative energy states, and unusual matter hold up. These are all important parts of models of how the universe evolved and how wormholes stay stable. Using very cold atoms and Bose-Einstein condensates in small tests on a table can also be used as analog models to simulate parts of bent spacetime, which can teach us a lot about how quantum effects work in very harsh conditions. These projects are moving forward thanks to the work of foreign space agencies, study institutions, and private businesses working together. In these partnerships, people with different skills and resources work together to create unified testing systems that can compare results from various observational and experimental methods. This global method not only speeds up technological progress, but it also makes sure that the data gathered is accurate and complete. As we come to the end of our talk about wormholes and the possibility of traveling between galaxies, we hope you're as interested in these strange ideas as we are. The fact that we can travel huge distances through space in the blink of an eye, go into the unknown, and change how we think about space and time shows how persistent scientific research is. Check out our other videos on the cutting edge of science and space travel. If you liked this one about the ultimate cosmic shortcut, please like it and subscribe to our channel for more. If you want to know about our newest posts, click the reminder bell. Also, let us know what you think about the possibility of wormhole travel in the comments below. Your thoughts and questions keep the talk going as we look into the universe's secrets.